So if we say we have a formula what I like to do is give you guys a method of going through and solving each type of problem, so that they're stepwise. You can see a stepwise thing, and then you can adapt that to your own needs. When we're doing stoichiometry, of a chemical reaction, there's going to be several ways of doing it, and like you have to get all the steps, but you don't necessarily have to do them in the order that they're presented. And so when you translate a reaction into a chemical equation, you're going to take the words that describe the compound and then change it to the formula of the compound. So we're going to have titanium 4 chloride and water to react to form titanium 4 oxide and hydrochloric acid. We did that. We're going to separate it into reactants and products. Of course, the reactants come first. That's what we're looking at. And then we have to find the stoichiometric ratio for each one. And we're going to arrange them into an equation. So we separate into reactants and products, we arrange into an equation, and then we indicate the physical states if we can. Now, to me, the physical states aren't as important as understanding what's reacting, because you can change the physical states in a reaction to suit your needs by changing the temperature or the heat, right? The temperature, heat, temperature, or you can add a catalyst. So balance equations by adjusting coefficients. So once we have the equation written, now we're going to adjust the molecules on both sides. And we're going to start with the elements that appear once on each side, balance free elements last, balance unchanged groups of atoms. So it's always, you always balance oxygen last, right? So because O2, N2, any gas like that, you're going to balance last. And we've already talked about balancing. We've already had some balancing. Here's the combustion reactions. We went over those. And then we were right here, I believe. So when we combust ethanol, we have C2H6O, right? So we're going to do C3H2OH plus O2, right? Because that's the structural formula, C3HCH2OH. And we have 2 C's on this side, 1 C on that side, so we're going to put a 2 here, right? That's the way I would do it. And then that we have 6 hydrogens on that side, so I'm going to put a 3 here, right? So now I have 3, and this would help if I had a tablet and I was writing on it, which I could do, but I didn't. So 3, 2 here, 2 here. Did I say 2 here? 2 here, and then 3 here. So that gives us 3 oxygens, 4, 5, 6, 7, right? And then we have 1 on that side, so we only need 6, so we put a 3 with the O2, and that's balanced. So we have 2, 3, 1, 2, 1, 3, 2, 3. Okay, and then the next one, calcium nitrate plus sodium phosphate yields sodium nitrate plus Ca3PO4, which is calcium phosphate. So this is what we call a double displacement reaction. In a double displacement reaction, we swap anions with cations. So the cation calcium will get the second anion phosphate. The second cation will get the first anion. So when we do that, we'll use our solubility chart to make sure that we know that all nitrates are soluble. So if we were putting our states in here, NaNO3 would be aqueous, and we'd look up calcium phosphate and we'd see that that is a solid. So otherwise there's no reaction, right? Everything just stays in solution. So these two would both be aqueous to start with. So calcium nitrate would be aqueous, sodium phosphate would be aqueous. And so we put an AQ here, AQ there, an AQ here, and a solid for calcium phosphate. So now let's do the math. Start with calcium, 1 on this side, 3 on that side. That's not gonna work, so we'll put a 3 here. Now they're balanced, they both have 3. So we have 3 calcium nitrates plus, let's just see, we only have 1 sodium here, so let's put a 3 here. That gives us 3 sodium nitrates. Uh-oh, that's not gonna work, because now we have what do we have here? 3. So that's 6, but we only have 3 here, so we need to make this a 6. Right? You with me?
Mm-hmm.
All right. So that's now 6 sodiums, so we need a 2 here. So what we have is 3, 2, 6, 1. Is that right? 2, 1, 2, 1. Where are we? No, 1. Okay, let's try again. So we have 3 here, we put a 3 here. That doesn't work. We have a 2 here, or 3 here, so now we have 6 of those, so 3. And then 2, and then 6, and then 2. Or no, just 1. Right. Yeah. Okay, so 3, 2, 6, 1. All right. So part of this is, right, visualization. A lot of chemistry is visualization. So try to see it. Write a complete balanced equation for the reaction of barium chloride. So second column, alkali earth, plus 2 charge, goes with chloride, right? And so it's going to make barium chloride. And then we have H2SO4, which is sulfuric acid, which is one of the 6 acids we should know. Barium sulfate is one of the products. And the other product would be what? The result of a double displacement. So if you make barium sulfate, you're going to make HCl. And in order to balance that, we have 2 chlorides and 2 hydrogens on this side. So this would be 2 HCl. And that would be aqueous. And that would make it an acid. So we're going to go from sulfuric acid to hydrochloric acid, another one that we should recognize. Right. Hydrochloric acid is a binary acid because it contains just 2 things. Sulfuric acid is a oxy acid because it contains oxygen. Always recognize if you can donate a proton like you can with H2, right? Like with H2, SO4, if you see the H2, you know it's going to donate a proton 2 times. We call that a diprotic acid. HCl is, you only donate 1, so it is a monoprotic acid. And phosphoric acid, H3PO4, would be a triprotic acid. And all that means is it donates a proton 3 times. So let's classify our chemical reactions. We have precipitation reactions, where we have, so what happens here is we have a metal cation plus a non-metal, oh, this one's messed up too. A non-metal ion, I went through and fixed all these. Non-metal anion, and it forms an MX compound. I guess I didn't fix it, I thought I fixed it. And this gives you a little bit more time to look at it too. Okay, so we have precipitation reactions. What happens here? We have 2 ions in solution. They come together, a metal and a non-metal, and they fall out of solution. That's a precipitant, right? So we have a metal plus a non-metal. And usually it's a double displacement reaction. Then we have acid-base reactions. We can recognize an acid-base reaction because we have a proton, H+. You always think proton when you think acid. And then OH minus, proton acceptor or a base. So acid plus a base is a neutralization. We also call it an acid-base reaction of neutralization. And we form water. Water gets a liquid state because this is new water. Even though these are both aqueous, which means there's water in the solution, when we actually form water doing a reaction, we put an L there, just part of the language, the nomenclature that we have to understand. But the L designates that we made that liquid in the reaction. And then finally we have oxidation reduction equations. And in those we take a metal solid at elemental state. Elemental state is always what charge? 0, no charge, right? It's like a neutron walks in a bar, asks for a drink, and said, how much will that be? And the bartender says, for you, no charge, right? So elements have no charge either, okay? And then we're adding oxygen to this, so what's gonna happen, the metal is gonna lose electrons, and the oxygen is gonna take them away, and it's gonna be reduced, right? If you lose an electron, you're oxidized, Leo. If you gain an electron, you're reduced, Gur, right? So Leo goes Gur, or Gur says Leo, depending on whether you put the cart in front of the horse or the horse in front of the cart. And then, so that's the types we have to recognize. And then we're gonna break these down even further and do half reactions on the metal and on the non-metal. Why do compounds dissolve? We talked about this in lab, so I'm gonna skip over that. If you wanna review, you can watch that at another time. But what we wanna make sure we understand about solubility is like dissolves like. So if you have a polar compound, which means if there's a charge anywhere in the molecule, you can break down another polar compound. But what doesn't like to happen is a polar molecule and a non-polar molecule, they don't mesh like oil and water. Oil and water is a perfect example. Water's polar, oil is not. So oil floats on water. Why? Because water has a higher density, so water's below, oil's above, unless you have a heavy oil, in which case they reverse places because density determines which one is on top, but they don't mix because they're dissimilar solutions. And then what kind of bear dissolves in water? A polar bear, and it was in labs, and I remember. All right. So non-ionic compounds also dissolve each other, right? So two types of oil will mesh together and form a homogeneous solution often, right? Which is one of the good things about oil spills on the ocean, right? If there is a good thing, there's two good things. One is that if it occurs non-naturally, the oil floats in the water, it doesn't dissolve in the water. And you have to find a way to contain it and pull it off, but it doesn't dissolve. But also the ocean, oil just flows up out of cracks in the ocean anyway, which I don't know what we're gonna do to stop that tragedy. I guess nuke the ocean floor and seal it up, I don't know. Okay. And though these are all problems for your generation, right? We made this giant mess, and it's up to you guys to try to fix it, just like we tried to fix the giant mess they left us, and we made it worse, so I don't know. Useful definitions, again, non-electrolyte, a solution that does not dissociate into ions. So when you take sugar, right, and you dissolve sugar in water, you're breaking the bonds between molecules, you're not breaking molecular bonds, right? So the molecule dissolves, it's held together. Sugar's held together by intermolecular forces, and you could break those forces by dissolution, but you're not breaking apart the molecule. So when you dissolve a sugar, it's not a chemical change. Okay? Electrolytes, a solute that does dissociate into ions, completely dissolves as ions. All soluble ionic compounds, all strong acids and bases are strong electrolytes. And that was our conductivity lab, right? That's why I said that in the conductivity lab. If you missed, did anyone get the numbers that I gave in lab?
I posted.
No, right? Oh, you did? Okay. Right, so whoever did. If you didn't post, I don't know how to do this.
I gave them to Brittany and she put them on the discussion board for on Canvas.
Right, I saw that. I saw it, and somebody else also, right? But did anybody else get them? Did anybody write them down when I was talking about it? So when I'm talking in lab, it's probably a good idea to write stuff down. I'm just saying. Here, not so much. Anyway, weak electrolytes. So strong electrolytes mean it completely dissociates. Weak electrolytes means it only partially dissociates. And when we partially dissociate something, we call it a weak acid or a strong acid. So acetic acid doesn't come completely apart. What's acetic acid? H, right? We should already know this, or at least recognize it, right? It's the choo-choo. I think that's what, right? What is it? C? CH3H2O2, is that what it is? No.
What are you trying to make?
I don't know, acetic acid, I forget how to make it now. Is it
It's like CHOO.
CHOO, like that? CH,
Yeah, it's like that, but with an H in front.
what is the acid?
Acetate is C2H3O2, I think.
Okay, so that would be this, and 1, 2, 2, then that, and then this, and then, no, that's not right. Cause this, oh, yeah, that's right. 1, 2, 3, 1, 2, and then 1, 2, 3, uh-oh, that's not right. What do we got? You guys don't, well, CH3,
C2H3O2, yeah.
yeah, but this is not enough bonds. Oh, this one? Yeah, there we go.
Da-da-da.
Da-da-da, okay. Right? So, if you put an H here, now you have acetic acid, right? You have acetate plus H. This doesn't come completely apart. So that means that some of these are, oh, let's do it right this time. 1, 2, 3. And these represent bonds. So this is, when you have the acid, this is what you have. And it's, what we say is, a lot of it stays like this, and some of it goes into H plus and this. So it partially dissociates. That's what we're looking at. When we do HCl in water, all of it dissociates. Right? Completely comes apart. There is no HCl. There's only H plus and Cl minus. When we say it's a weak acid, it means some of it stays in this state. Some of it goes to this state. All right? And that's based on how much of this there is, right? That's the pH, and the concentration of H plus can change, and it will always stay in the same ratio. But if you take this away, then more of this will go that way. And that's the basis for weak acids and buffers and all kinds of things that we're not going to talk about yet. All right, so how to indicate that compounds dissolve and also dissociate into ions. So for non-electrolytes, right, like sugar, right, we dissolve it in water and we just write sugar aqueous, and that would be that C6H12O6, right, and you just dissolve that. But you're breaking bonds between the molecules, you're not breaking the molecule. In electrolytes, sodium chloride completely dissociates into sodium ions and calcium ions, calcium chloride, calcium ions plus chloride ions. Acids dissolving to release protons. So a strong electrolyte, like HCl, completely comes apart into H plus, Cl minus, right? And then weak electrolytes only come apart slightly, and then we have an arrow to indicate which one is more favorable. So in this reaction, because the long arrow is toward the complete molecule, right, the H plus C2H3O2, right, it stays over here more than it comes apart. But you can fix that by taking away the acid part. Like, so if you neutralize the H plus, more acetic acid dissociates. Be aware the number of ions formed when an ionic compound dissolves depends on the formula unit, right? So we already did this before as well, right? So if we have, how many ions are formed when ammonium phosphate dissolves into water, we get the 3 ammonium ions plus the 1 phosphate ion, so 4 total molecules dissociate. So that's going to be so you can take one molecule, you're going to have a complete dissociation with 4 molar ion concentration, right? And we can calculate how much of that is dissolved, how many moles of ammonium ion will be produced, and we could do that if we had 0.216 grams of ammonium phosphate. Using the molar mass of 143.1, we convert to moles, and then we say there are 3 moles of ammonium per 1 mole of ammonium phosphate, and that gives us 4.52 times 10 to the minus whatever that is, 2. Which is not a lot. It's not a huge concentration, but it is calculable. And why would we want that, right? Well, we may want to do a reaction with ammonium, right? May want to put ammonium on something and then precipitate it out, which we'd have to change solvents, right? Because that's one of the things that happens. If you understand that something dissolves in water, but you want to claim it as a solid, you have to counteract the amount of water and make it fall into a different phase. So you put water with a nonpolar solvent like methylene chloride, shake it up, and the nonpolar part would go out of the water, right? And go into what we call the organic layer. But that only happens without ions, right?
So would you be so if you have a solution in water, how would you show, say, if you boil off all the water in a chemical equation to show like it started, it should be aqueous, but because I boiled it, it's now solid?
Yeah,
How would you
that's reasonable.
show
So there's two ways usually. The most normal way that we don't really show that as an equation. It's just kind of understood. But if you had HCl, right, aqueous, right, you would show it as, and then you'd put it like a delta H or delta T, right, and that says boiling.
Okay.
And then you just say
put it as
HCl solid,
Okay.
right? You're not precipitating it out. You're removing the solvent and you're reassociating the ions.
So it's the delta T symbol that shows that it's being
Yeah, it shows heat.
heated.
Yeah,
Okay.
change in temperature, right? You can also do it by freezing as well. A lot of times any kind of change in temperature changes the relationship and the solubility. The number of ions formed when an ionic compound dissolves depends on the formula unit. So we already talked about that. How many ions are formed when NH4? We just did this, right? 3 NH4, 1 PO4, so 4 total ions. And we just did that, and we went through that. And precipitation reactions. So we're going back to, we're gonna do a double displacement. Two solutions, we pour them together, something's gonna come out. And what's gonna come out is M plus X minus coming together to form a solid MX. And we're gonna switch cations and anions. One of them is gonna be soluble, one of them isn't. They both start off soluble in water, but when they find each other in a solution, they're like, oh, I much prefer you to water. Let's drop out, and they do, right? And they form a precipitate. So here's what we call a beaker drawing. So if you're ever asked to do a beaker drawing, all that means is you don't have to use the colors, but it's kind of cute, right? So you have M plus in there, X minus, they come together, going back and forth, and then they drop out. This is supposed to be insoluble, the yellow, right? So you can reach a layer of, so the other thing this is saying is based on concentration, the more you put in, eventually you'll hit a limit where you can't dissolve anymore and it'll precipitate back out. So you put a solid in and it'll come apart and then go back together because there's too many ions in solution, and so some of them precipitate out. This is without even an exchange. The rule of thumb is when the maximum solute concentration, right, the part that's being dissolved, the solute, is less than 0.1 molar, a solution is considered insoluble. So some solutions are insoluble because when you put in less than 0.1 molar, it doesn't dissolve. Okay, 0.01 molar. Does that make sense? Predicting whether a precipitate will form. Note the ions that are present in the reactants. Consider the possible cation-anion combinations. Decide whether any of the combinations are insoluble. So we're switching, right? Product for reactant, or cation for anions within the compound, right? And then we're determining if either one of those combinations is soluble. And if it is, we have a precipitate. If you exchange a nitrate for a nitrate, both are soluble no matter what they're attached to, so there won't be a precipitate, there's no reaction. You just have 4 different ions in solution. If one is a precipitate, right, then you're gonna leave 2 ions in solution and 2 of them are gonna come out as a compound. And solubility rules, here are the solubility rules, we went over those before. Remember, if we look at nitrates, all nitrates are soluble, all acetates are soluble. That makes them very good for doing precipitation reactions, right? Because whatever they're going to attach to, you can deliver to something else, right? Because you don't have to worry about making an acetate precipitate by accident. And then other compounds are completely insoluble. So anytime you have sulfur, with these few exceptions, right, it's going to precipitate out. So that's why in the early days of chemistry, you see a lot of sulfur compounds. That's why the early days of drug discovery, there were a lot of sulfur compounds, including thalidomide, which was a sulfur-bearing compound that was given to pregnant women and ended up causing birth defects. And then we found out, right, we followed the science and found out that they're handed molecules, and that one hand does one thing and the other hand does something else. And so because of that tragedy, we learned to separate what we call enantiomers, which are different handed molecules, right? And then that opened up the door to all kinds of better medicines because we didn't have the side effect of the opposite hand, right? We didn't know, nobody knew, it seemed like a good idea. We also have a whole bunch of sulfur drugs that are very good at killing infection. So you just have to be careful, right? And you don't know when you're saving the world that part of what you're doing is not saving the world, right? So you have to be very careful. And one of the things that has to be translated, especially in today's world, where we're solving problems and we seem to be solving problems without saying, okay, what are the possibility of effects down the road, right? We need to stop it. Like, so when it's raining and your roof is leaking, you get up there and you stop it from leaking. That's the part you're supposed to do, right? Then, once you've solved the leak, then you go back and try to make the roof look pretty. But you can't be held responsible for whatever happens while you're sealing off the roof, because you've got to stop that leak. And that's kind of what's happened in our whole virus contagion world. Is in the forefront, we're stopping things. We don't know what the later effects are going to be, because we have to stop this transmission. We have to keep people alive. Now, some of the people later are going to have effects, and it'd be a lot better if we got in front of that and said that up front. Look, we don't know what's going to happen. This is our best bet. We're fixing a leaky roof, and some things aren't going to turn out right. And that's why they released liability for all the drug companies that provided services during COVID, right? Because everybody knows there's going to be something that goes wrong, because you're fixing a leaky roof, and if you don't fix the roof, you're going to get flooded. And we didn't really get flooded. So if you step back a little bit and look at the big picture, when we're fixing things in the forefront, big problems, we're trying to limit the damage. And we really did, because instead of being 20 million dead, it's 1 million or so, right? So we have to, it doesn't affect, if we lost people or there are people that are going to be affected down the road, we can't do anything about that. But we have a lot of people doing the very best they can, and I feel like they need our support. All right, so solubility, sulfonamide drugs, right? Always soluble compounds. Whenever we're looking at nitrates or acetates, those are the ones I always keep in my mind, nitrates and acetates. And nitrates are especially problematic when it comes to drinking water, because they're soluble in everything. We have systems, membranes that will trap nitrates, so that's good, so we can get purified drinking water. One of the side effects of agriculture is production of nitrates, and in order to drink the water, we need to separate the nitrates, because it's one of the problems with drinking wine is nitrates. So we have mostly soluble compounds, right? That means more than 0.1 is soluble, 0.01 is soluble. Chlorine, bromine, iodine salts. So these are things that you would think of if you were trying to synthesize compounds. How do I deliver them? How do I get them out of solution? Oh, I attach them to an iodide, I attach them to a halogen, and now they're going to come out of solution. So one of the, in organic chemistry, when they're trying to go from starter drugs like stay on this. SO4 salts, so sulfates. Sulfates are really insoluble normally, except for what? When it's an acid. But if you use sulfuric acid, it's a good way to deliver sulfate, right? Because you've got the protons, you've got them separated in ions. Now that's free to exchange with anything else in solution. And that's what we're really looking for. And then you have mostly insoluble compounds like carbonates, hydroxides, phosphates, and calcium, strontium, and barium salts with hydroxide. And they have a little bit of solubility, modest, right? So they're partial. So predict which ones will form precipitates in the following reactions. So we're going to do a double displacement, right? That means the calcium is going to go with the nitrate, and silver is going to go with the chloride. And then we have to balance that out, right? So we're going to write, let's just do these. And I'm going to go a step further with these. And I'm going to introduce one of the next topics, because this is a good place to do it. What is that? All right, we're supposed to form a reaction here. And what we're going to do is we're going to put the opposite cation and anion together. So we're going to put calcium nitrate. Right? Calcium's a 2+, nitrate's a 1-, so we need 2 of them. Right? And then we're going to put silver and chloride together. And that's going to come out, right? We just got done saying chloride compounds are slightly insoluble. So a halogen's a good way to get something to come out of solution. A good way to deliver a silver to have it come out of solution is with a nitrate, because all nitrates are soluble. If you learn one thing in this class, all nitrates are soluble.
Question.
Yeah.
When finishing the equation, why do you start with the calcium nitrate instead of silver chloride? What makes calcium come
first?
Yeah.
I don't know, because I started with.
So there's not a reason why they can be switched.
It's just a what is that called? A convention.
Okay.
But yeah, it can be switched.
Okay, got it.
But this is the preferred methodology.
Okay.
Anyway, I just do it that way, and I'll also do the precipitate last. It's just my own way of doing it. I don't know if that's a convention or not, but to keep it going the same way is usually the convention. All right, so this is our solution. We look up silver chloride on the table, and we see that it comes out as a precipitate. So the next step is what happens during that, and that's where you can draw beakers, right? And you say we have Ca2+ and NO3- and Ca2+ and NO3-, and then at the bottom, right, we have the associated silver chloride molecules, right, dropping out of solution. And this would be like a beaker diagram, a bad one, but I mean, I don't really put a lot of stock in them, except for they do show what's still in solution and what comes out, right? And you can even say, okay, we have an Ag+ with a Cl- and it precipitates out. So that's what happens in the beaker. But so let's make that happen next. And when we do that, we call it the complete ionic equation. All right, and for me, the complete ionic equation starts, and I'm going to just keep them all the same color. Ca2+ aqueous, so we're dissolving this in water. 2Cl-. Why 2? Because this says there are 2 chloride molecules. This says there are 2 chlorine- anions once we dissolve that solution, right? So when we're looking at this calcium, it's calcium with a Cl and a Cl, right? And these Cl, this ionic bond is going to be broken by H2O, right? And we know that the positive side of the H goes towards the negative side, and the negative side of the oxygen goes towards the calcium. That's what dissolves it, right? The water surrounds that ionic bond and shows more interest in the partner here than the cation does. So we dissolve that, this becomes aqueous, and we keep track of the states. So 2Cl minus, and then we're gonna go to the other compound, silver, and we have to balance that. So now it's balanced, right? All right, you start with a balanced chemical equation. Same number, 1Ca, 1Ca, 2 Cls, 2 Cls, 2 silvers, 2 nitrates, 2 nitrates, 2 silvers. Okay, so that's balanced. This comes apart on the reactant side, AQ, and it's a +1. And we know it's a +1 because there's only one nitrate molecule. And then what else is over here? Nitrate. And there's 2, I'm sorry. 2 of those and 2 of these, and then it's aqueous, right? So the coefficient is how many of those molecules are in the balanced chemical equation, and it should be more specific, that's ions, how many ions. And let's make that 2 real, a real 2. Yeah. All right, so we have the ions, all the reactants are taken apart. We go to the product side, calcium 2+ stays in solution, right? Because it's still aqueous, and aqueous says that it dissolves the ions, right? So we're gonna come completely apart, and then there are 2 nitrates, so the nitrate comes apart, and that wasn't a bad 2 aqueous. So 1 calcium, 2 nitrates in solution. This is a minus, right? A 1 minus, and that's why you need that to either memorize or have that chart of charges. Right? And then what happens, and I'm going to leave this a different color, is we made 2 silver chlorides, right? 2 silver chloride molecules. So what's the difference between this and this? These two equations. The silver chloride is a solid. That's what we're showing. We're showing the change in the reaction from the reactants to the product. So when we have a precipitate, we write the entire precipitate. So that's the complete ionic equation. We dissolved everything, the reactant compound, each reactant compound. We showed the product that's still in solution, right? Like still here, the ions are still in solution. And then the precipitate stays together. So that's gonna be the change. And when we look at the change, we call that the net. Whoa, that's bad. The net ionic equation. All right? And when we look at the net, what we're doing is we're saying what changed. What stayed in solution, what changed. So we'll look at each side of the equation. We'll look at the first reactant, calcium 2+ aqueous. We come to the product side, and by gosh, it's exactly the same, right? So no change there. Then we go to 2 chloride minus, the anion. And we come to this side, and holy, look, it's in part of the precipitate, so it did change. So we're gonna keep that. So we're gonna write that down. 2Cl minus aqueous. We're gonna go to the next part, silver. 2 silver plus 1 on this side, and compound on that side. So we bring that down. We go to the nitrates, 2 nitrates on this side, 2 nitrates on that side, so they cancel. Right? And we're left with 2 silver chlorides. And a little bit of art there where I made it red and black. All right? So that's actually a much better color. Anyway, this is our net ionic equation. We take 2 chlorine anions, 2 silver cations, and we make 2 silver chloride molecules. And so that's the net ionic equation. The net ionic equation is a change in ions into a precipitate. When we make the precipitate, it stays together, both in the complete ionic equation and the net ionic equation. All right. So this type of reaction is called double displacement. Sometimes people call it double replacement. Depends on where you're from. All right, so that's the first one. The second one would be potassium acetate plus iron sulfate. State is aqueous. I assume that's what it is. Aqueous. All right. And now we're going to do a double displacement. We're going to put these two together and these two together. So we're going to start with what comes first to me, and let's go.
Potassium sulfate.
Yeah, let's start with potassium sulfate. Sulfate is a 2-, so we need 2 potassiums to form the compound. Remember, we form the compound first by charge balancing, and then we determine how many molecules there are. Once we form this compound, right, we cannot change the ratio of the elements. The elements are in it, and they have to stay put once we form the compound. The only way we can change the number of potassiums now is to put a coefficient in front. So the second part then is iron acetate. Whoa. Huh. Iron acetate. And this would be C2H3O2 3 times.
Now we balance it.
And now we have to balance, right? So we have 2 potassiums on that side, 2 potassiums on that side. That looks good. Uh-oh. 2 irons here, but only 1 iron here, so let's put a 2 here. Now we've got that right. Sulfates, we have 3 here, but only 1 there, so we'll put a 3 here. And now we have to look at our potassiums. We have 6 potassiums here, so we need 6. What? Wait a minute. It's not K2. It's just K. I know, right? Dummy. Whoa. That's K2, no? All right, so let's just restart. Get your compounds right. I can't believe I wrote that like that. All right, K, so 1 here, 2 there, 2 here, and 3 there. So we're still gonna have some problems. So let's put a 2 here, and now we'll come back and we have 6 here, and that's gonna make this a 3. And what happens here? 6, 3, if we put a 3 here, that's not gonna work. What? Hold on. Start again. I have a little trouble with this one now, apparently. Did I set this up right? Yes. Okay, so I have 2 there, I put a 2 here, I need a 6 here. So I have a 6 here, so I need a 3 here. And now we're balanced. Okay. All right? Now we have to look up which one of these is soluble. But I happen to remember all nitrates and all acetates are soluble, so that means this is the AQ, and therefore this is the, but is it? We have to look on our chart, because I thought potassium compounds are, do we have our chart? Can anyone look that up and see if that's soluble? Sulfate salts, except with, strontium, I thought all of them.
Sulfates are generally soluble. Exceptions.
Right, so that's not an exception, right?
Nope. So it's soluble.
So it's soluble, so what does that mean? What does that mean?
No aqueous.
Right, no reaction, right? Because what happens in our jar?
Everything cancels.
Everything's just in there. K plus, C2H3O2 minus, SO4, 2 minus, Fe3 plus. They all just stay in solution. So you mix them together and, oh well, not today, no reaction today. And so that's why we have that solubility chart. But let's not make the mistake of saying that's predicting. That's not predicted. The solubility chart isn't predicted. It's observed, and then reported, and then we use that to compare. It's not like we had a theory that says why these certain ones are soluble. I'm sure there is one, but we don't get into it in this class, and I pretty much never looked at it in the entire time I was getting my degree. Although now I'm very curious as to where it came from.
So even if there's no reaction, we wouldn't finish with a complete equation or net ionic because it all cancels itself out?
Well, because there's no reaction.
Okay, got it.
All you're doing is freeing, you're just dissolving, making electrolytic solutions.
Okay.
Yeah. So there is no complete ionic or net ionic because nothing took place. There's no precipitate to
Yeah.
change.
So a homogeneous mixture.
Of of ions. It would have a good conductivity. Guess I'll lose that. All right.
There's one more.
One more. And that would be, oh, why did I change the page? Last one is copper, nitrate, and sodium carbonate. And we already know which one is going to be the possibility, right? Because if you've listened to me at all today, you know all nitrates are soluble. So copper 1 nitrate is aqueous, right? Because they're both going to start off aqueous, and then, oh, I already forgot. Sodium carbonate. Okay, so to do the double displacement, which we're still doing, we do with all solutions, we're going to swap ions. Copper goes with carbonate. Oops. And then sodium goes with nitrate. And all nitrates are soluble, so we know this is AQ. We look up and carbonates are not soluble very often. So we have that, forms the solid. Now we just have to balance. We need 2 here. We have 2 there, so we're gonna put a 2 here, and now somebody needs to teach this guy how to write 2s, I'm telling you. Okay, 2 there. Okay, so now we're gonna do the complete ionic equation. We're gonna split all these guys up, into ions. All right. Excuse me. Can't you just turn that thing off while you're in class? No? Okay. 2 copper plus 1 AQ plus, I'm gonna break this nitrate up into a molecule, anion, excuse me, and then 2 sodium plus, and this, I mean, like, you get so tired of writing aqueous, it's unbelievable, but it does help you understand what's going on. Oh, maybe. And remember, the solid stays together in the complete ionic equation, and so let's keep it together, and then this one comes apart, aqueous, and we have hand-eye coordination problems. All right, it's because I'm left-handed. 2 NO3. You know, in the old days, the nuns would slap your hand. That's where I learned to hit back. Thanks, nuns.
Why?
Okay. Net ionic equation. All right. So we're going to take what changes. So we start with copper on this side as.
Don't throw it.
No,
Throw it.
I'm too mad.
Just the anger walk.
So you have 2 copper ions here. On this side you have a solid. So we can bring the solid down, Cu2CO3 solid, and the copper down, 2Cu. Wow. AQ. Then we look at the nitrate on this side, nitrate on that side, cancels, sodium on this side, sodium on that side, and we're left with the CO3 2 minus, converting to the solid product. So our net ionic equation again is what changes in solution. We're going to put the cation and the anion together and make a compound. Maybe I just take the time when I do it to do it. I don't know. This many years, it's not going to change. All right, so we have double displacement reaction. We're switching cations and anions between the reactants. One of them is going to form a solid, otherwise we don't have a reaction. Yeah, Nathan.
In the complete ionic equation on the left side of the sodium, why is it 2 of the sodium and not a single? But it doesn't matter for the CO3.
The CO3 is a 2 minus,
Oh, I see. Okay.
right? So to charge balance this compound, we need 2 sodiums. Yeah, good question. All right, one other thing. When these guys stay in solution, we call them spectators because they're just watching the action, right? They're not participating in the action, they're just watching like a unit or something. Anyway, let's keep moving. So one thing, if you don't know about me, is my jokes are for me alone. And if you happen to find them funny, good for you. But anyway, the molecular equation shows all the reactants and products are. I may have a meltdown of laughter. Shows all the reactants and products intact. Spectator ions, right? The ones that are not involved in the reaction do not participate in the net ionic equation. Only what is active takes place in the net ionic equation. The change in chemical reactivity.
At the end, when you get the solid.
Yeah.
So copper has a 2 charge, or it's just the.
How many coppers are there here?
There's 2 coppers in it.
Yeah, so, and this is the CO3 2 minus.
2 minus.
So this, we have to spread that 2 minus over 2 coppers, so each copper still is copper. So, just one. So a double displacement, great question, because it leads to, we don't change, this is not oxidation reduction. So whatever the charge is that starts with the ion in solution, stays there in the completion. You're not exchanging electrons, you're exchanging ions, right? Where in oxidation reduction, now the metal's going to change from reactant side to product side. Yeah? Great, great lead. So here's $5. Thank you. Make my lectures interesting. Give the molecular equation for the reaction. Here we go, another example. Give the molecular equation for the reaction of lead nitrate and sodium iodide to form solid lead iodide. Oh, so at least this one they give you.
Yeah, you don't sell it.
One more, and then I'll put the slide up. I bet it's on there, but it's all right. Because it leads to another interesting thing. That in my own slide, I didn't do it. Golly. So lead is one of those variant compounds where we don't know what it's going to be, right? So if I say lead, well, let's see if I put it in there. Let's just put it up. Well, after I put it up, right? So lead can be either 2 or 4. In this case, I'm using it as lead 2, right? So this really should say lead 2 nitrate.
It's like the names look like Columbus or something, right? So that too.
Yeah, the smaller of the 2 charges is us, the higher the 2 charges is ick. So plumbic would be lead 4, plumbus would be lead 2. Lead 2. NiA, sodium iodide, and then we're going to make remember, double displacement, so the charge on the lead isn't gonna change. We're gonna have PbI2, and that's gonna be the solid. And then so, again, now this is gonna be NiNO3, and to balance it, 2 here, 2 here, and that's our double displacement reaction for lead nitrate. And you can practice on your own, break it down if you want. Yeah. Whoa, we're doing pretty well. It only means I'm gonna have to lecture for an hour in lab, not 2 hours. So, we just got. Dude, it should be instantaneous. Come on.
Nothing ever is.
Nah, you gotta wait for the good stuff. All right. So, molecular equation shows all the reactants and products and unassociated compounds. All right. That's just unbelievable. How could that even be in my slide? Shows all the reactants and products is intact and unassociated compounds, right? Our complete equation shows states only, but infers that all the compounds have not yet been dissolved. The aqueous says they're dissolved, but the molecular equation does not. Example, give the molecular equation for the reaction of lead nitrate, lead 2 nitrate, and sodium iodide solutions to form solid lead 2 iodide. So we start with the nitrate, and we show them as the compound without dissociation, and we indicate the state of the precipitate. Okay. Then the next thing we do is the complete ionic equation. That's where we take the compounds apart as they dissolve in solution. We can make a beaker diagram if we so choose. I don't know, I think we do in this class at some point, do a beaker diagram. Or maybe I didn't have you do it. Shows all the soluble ionic substances dissociated into ions. So we have lead 2 nitrate plus 2 sodium iodide aqueous yields lead 2 iodide solid and 2 sodium nitrates. Because remember, all nitrates are soluble. So Pb2 plus aqueous plus 2NO3 minus aqueous plus 2Na plus aqueous plus 2I minus aqueous yields lead 2 iodide solid plus 2 sodium aqueous plus 2 nitrates aqueous. Right? We're going to mark the change with the spectator ions, right? The ones that don't participate but just watch. So we have sodium plus, nitrate minus on both sides of the equation are unchanged and therefore are the spectators. The net ionic equation eliminates the spectator ions, so whatever doesn't participate, whatever remains in solution in our beaker and doesn't precipitate out, falls out of the nitrate ion, falls out of the ionic equation, the NIE. Pb2 plus in red plus 2 nitrate minus aqueous plus 2 sodium plus aqueous plus 2I minus aqueous. The red font shows what's going to be the net ionic equation plus 2bi PbI2 solid. That's going to be our precipitate, and it has the solid designation, and we cancel out the spectators, and we're left with Pb2 plus aqueous plus 2I minus aqueous yields lead 2 iodide. And canceling is just algebra. We have another set of examples. I'm not going to do those. But what is going to be, okay, what is going to be the switch? The switch is going to be between nickel and sodium, where they're going to switch. So we're going to make nickel carbonate and sodium chloride. And if you think about sodium chloride as salt, we know it's going to stay in the water. So that means the nickel carbonate is going to precipitate out. If we have silver nitrate, all nitrates are soluble. So we're going to make silver chloride, which is going to be insoluble, and calcium nitrate, which is going to be soluble, because all nitrates are soluble. If you learn one thing in this class, all nitrates are soluble. So ammonium chloride and sodium sulfate, they're going to swap, and you're going to make ammonium sulfate and sodium chloride. And we know sodium chloride is soluble, but we don't know if ammonium sulfate is, and we'd have to look that up on the table. Okay. and then go through, take them all apart, do the complete ionic equation and the net ionic equation. Okay, so we finally made it through March 10th, and we're only at March 17th, so,
16.
Oh, my.
no, 17th.
17? Oh, it's 17.
Yeah, that's why we're all wearing green. Remember, St. Patrick's Day is not the 16th.
My watch is a day off.
That's nice.
I wore
But you know, somebody thought it was yesterday when I was at Santa Barbara walking on the beach, a homeless girl goes, "Is it St. Patty's Day?" And I go, "No." She goes, "Oh, well, have a Guinness for me anyway." And I was like, "Yeah, that sounds good," but I had to ask, so I didn't do it. But I love Guinness. You know, the brown, foamy, thick ale. It's just nice.
Irish Carbon.
Yeah. Okay, so we still have 10 minutes, so I'm going to switch to, unless you'd rather me do it in lab. Would you rather switch to lab now, or do you want 10 minutes here and then
Let's go to lab.
lab? Okay, sounds good.
My freaking lab book is
Spent my stuff out, but it also gave me a bunch of stroke allergies.
It's like,
Oh, you had to.
I don't know, it just started rolling.
it's not gonna go back into the home.
Wow. All right. We're supposed to print out a test. Is it still spitting stuff out, or was
No,
did it
no, it
finish?
stopped. It got me like,
That was okay.
All right, so we just got done covering, and here we go. Right? We just got done covering what kind of reactions? Double displacement reactions, right? Where we're switching anions and cations. Acid-base reactions are similar, right? But an acid is a substance that produces H3O plus ions. Now, let's not get lost in the difference between H plus and H3O plus. In the old days, we kept it super simple because we didn't need to obfuscate stuff. We were trying to explain stuff in a simple manner. It may not seem simple to you guys, but to somebody who spent hundreds of thousands of hours on chemistry, H plus, OH minus is simple. It's a little more complex to say it takes two water molecules to make H3O plus and OH minus. Still the same idea, just a little bit of spectroscopy changed the way we write it, and people find that helpful. So H3O plus is just H plus, but it's called the hydronium ion instead of H plus, instead of just a proton. Okay, and when it's dissolved in water. So a monoprotic acid, remember we said that delivers one proton. So we could do HCl, breaks apart into H3O plus and Cl minus in the aqueous, which means it's grabbing a water molecule. And then H plus Cl minus associates. A diprotic acid does it twice. And again, I've got H plus here because that's the way I believe it should be presented. And then H3O plus is just in the background of your mind. The hydronium ion is what they call it today. But really, it's still just a proton being delivered. It's being delivered via water. The diprotic acid means there's two protons, H2SO4, loses the first proton, becomes HSO4 minus, right? Because we took away one of the plus charges, so now it's a minus anion. You take away the second one, it becomes sulfate, right? So one way to deliver sulfate is in through sulfuric acid, and guess what we're using today? 6 molar sulfuric acid to deliver a sulfate ion to our copper. And then we're to replace that with zinc. So a triprotic acid, H3PO4, phosphoric acid, can lose up to 3 protons. Each one, so this one doesn't completely dissociate, right? You can see it has this arrow going the other direction. That's an equilibrium arrow. That's what we call that when it goes back and forth, dependent on concentration. So equilibrium is dependent on concentration. This proton comes off. This part of this monoprotic hydrogen comes off H3PO4 completely to dissociate into H2PO4 minus. You completely lose that. It's one way. It doesn't go back on. But the second proton, depending on where you are in the equilibrium, or how much dissociates, it goes back and forth, stays constant in equilibrium. So some of it comes off and some of it goes back on. And then finally, the same thing for the PO4. So what we say is dependent on the acidity of the solution, how much of the proton comes off. So this part of The first one is completely dissociates, but the second two are weaker acids. They still deliver the proton, but it takes more energy to get that proton off. All right. A base is a substance that produces OH ions when dissolved in water or accepts protons. So ionic hydroxide compounds, so remember OH minus is hydroxide, dissolve directly to give OH minus aqueous. So if we use this M, which is any metal, give up protons, give up electrons, which means the hydroxide anion. Some compounds accept H plus to indirectly give OH minus, and that would be ammonia plus water forms ammonium ion, right, and OH minus. So let's do our calculation, right? So on this side we have one N, on that side we have one N. On this side we have 5 H's, and then 4 of them are here, and 1 of them is OH minus. And why? Why can that happen? Because water does what we call self-dissociation. So it can be what we call amphoteric. So H plus OH minus can do this. Water can do this, right? It goes back and forth between H plus and OH minus. Not all at the same time, but a little bit dissociates all the time. There's always a percentage of H plus and OH minus, and that percentage creates a temporary, what we call dipole between the next water molecule. Remember, a dipole, if we say is a slightly negative charge here, slightly positive charge here, and that would lead to a charge here, right? And that would be the dipole. So this is negatively charged at this end of the molecule, positively charged at this end of the molecule. So that is going to create a dipole here at this positively charged one, and here, and then we have our O, and then this side is going to attract an O and make it negatively charged just because this is temporarily positively charged. On this side, this is temporarily negative charged, which is going to cause another molecule to dissociate when this one reassociates. So you constantly have this back and forth between H plus and OH minus. You might see it like this. Right, which I said is they're just doing that to confuse people, right? This is H3O plus and OH minus, still the same amount, right? 4 hydrogens here, 3, 4 on this side as well, right? So this is called the hydronium ion. I like to stick with the proton, keep it simple, right? When I test you, I won't expect you to do hydronium ion. If you move forward, don't expect you to know hydronium ion, but just need to make that little distinction. So ammonia can be transformed in water. So that's why when you pour ammonia into a bucket, you make ammonium ion. And then if you were a real smart guy, you would put nitrate in there, and then you can make fertilizer. And then we'll stop there. You need to recognize common strong acids and bases, right? And again, we're HBr, right? We went through the naming of that, and that's a binary acid. So H becomes hydro, and then the name of the non-metal with the ic at the end. So hydrobromic. HCl, hydrochloric. HI, hydroiodic. Then we have our oxyacids, right? Oxyacid because it has an oxygen in it. Hydrogen nitrate or nitric acid. Hydrogen perchlorate or perchloric acid. Hydrogen sulfate or sulfuric acid, right? Okay, so we can recognize those are all acids, right? Key for strong acids is they have an H plus combined with a halide, and then we have our symbology, which again, I prefer it the other way around. I prefer to know the compound and then go, okay, yeah, E-O-M, McDonald's had a farm. Anyway, N and below, S and below. So is CH4 a tetraprotic acid? No, not all compounds containing H are acids, right? And then is H3PO4 stronger than HNO3? No, acid strength does not equal number of protons. So just because I can deliver, or I'm a triprotic acid, doesn't mean I'm a stronger acid than one that delivers one proton, right? And what's more important is how accessible is that proton? How easily does it come off? What's the energy between the acids? And that's why nitric acid is especially strong, is because nitrates are especially soluble. They're attracted to everything, but they don't stick, right? So that's the thing with nitrates. Unlike some other bases, which will not let go, right? They find one thing and they hold on forever. So common acids are citric acid, acetic acid, aspirin, lactic acid, phosphoric acid, muriatic acid, which is really just HCl. So, and you know where you can get enough, where can you get enough HCl to do whatever you want? Ask the girl with the pool, right? Muriatic acid. Anyway, use it in pools. So sulfuric acid, we make 200 million tons of sulfuric acid. That's a lot. That's a lot. Like, you know, right? If you think of like F-250s or Cummins diesel 250s, that's 200 million of them filled up every year. Anyway, all right, more than that, because those are 3/4 ton, so it'd be more than 200 million. Anyway, common bases are bleach, right? Sodium hypochlorite, and then sodium bicarbonate, magnesium hydroxide, ammonia, and sodium carbonate. And that, well, I was in Wyoming, so these slides were made way back when. And the material's still the same. We're making 40 million tons of sodium carbonate, which is Trona, it's mined. There's another place like we make borax, which is right outside the California desert. So one of the things that you can look up as you get more interested in where things come from, or mines, or what is being mined and where it's being mined and how much of it. It's very interesting to try to put into the world perspective, right? So right now, lithium, which is not a very common element, is being mined, right? And there's only really 2 big places where they mine lithium in the world. And that 200 million tons, the total output is supposed to be around 80 million tons for batteries. So the supply is not much greater than that. So we can't make it for very long. So until we come up with a better way of these batteries, we're going to have all these lithium batteries that we're going to need to reclaim the lithium to remake the battery. And so far, every process that we've ever done where we reclaim something makes it more expensive, right? So if you think an $800 car battery is expensive now, just wait a few years. All right, so very few people will actually end up driving, right? I'm not trying to say this to be negative, it's a challenge, right? Because the cost is going to be prohibitive, just like buying a house. It's going to be prohibitive unless you're on this side of the wall. And how do you get to this side of the wall? Education, finding out information, applying that information to the society in which you live. And everyone is capable of it. It's hard, it takes time, but it's so worthwhile because you could be the hero of your entire DNA tree, right? Because you could set your family on the other side of the fence. And then you can worry about what you had to do to get there, right? Or the other side is to say, okay, I accept this, the universe wants me to be here, and I'm gonna stay here and do the best I can, and that's also acceptable. But what I like to think is that if the information is available to us as a society, as individuals within a society who have self-determination, we want to get that information. All right, sorry about that. Strong acids completely dissociate to produce H+. Okay, we keep saying that. Strong acids separate into ions. HCl is a strong acid, so it's going to separate into ions. And again, we form the hydronium ion and Cl. Strong bases completely dissociate to produce OH minus. So sodium hydroxide is an example of a strong base. It's also called lye. It's also used in the production of soap. You don't want to touch it with your fingers. It feels good though, like it just softens it. Anyway, you don't want to touch it with your fingers because you could use too much. So one time at Cal Poly, when I was fooling around over there, one of the chemistry majors swallowed a bunch of, she had a particularly weak moment and swallowed a bunch of sodium hydroxide. And it was the worst possible way to harm yourself. Chemical ingestion is not a pleasant way to say goodnight. So everybody has moments normally, mental health moments, and you want to be careful what happens during those moments. And I would say that if ever that happens to you and you're not prepared for it, reach out because somebody wants you alive, right? Most of us, really. None of us want to lose anybody at all. So be careful when you handle chemicals, right? You don't. So what happens with a base on the inside of skin is it eats it slowly, right? As the concentration shifts, your body carries it. I'm sorry to share that, but at the time I was young and it didn't affect me as much as it does now, right? Those kinds of things where somebody's so close to a program I was in and I didn't have the tools, we didn't even talk about stuff like that then. And now I think, we try to release the stigma. That's one of the reasons why you get educated, is so you can talk about the things that nobody talks about and then have a decent discussion and be prepared. And if I've crossed the line, I please forgive me, but I think it's important, especially coming back to society right now, that we open ourselves up to these things and try to deal with it, because somebody we know right now is probably in crisis. And so, okay, well, so weak acids don't completely dissociate, right? Strong acids come completely apart, strong bases completely apart. So you don't want protons floating around in your body, you don't want hydroxide ions floating around your body if you can help it. Now, you drink water and it's going to dissociate, right? Some of it, but not in a large enough quantity to affect your body. But you can definitely change your pH within your body in a certain range and stay healthy, right? Your body can take things up to like 9.5, pretty much pH, which is a measure of loose hydronium ions. It can also go the other way down to about 6.5, and you can still be pretty good, but really we want to be around 7. And when we ingest things that are around 7, usually we feel pretty good. When we ingest things around 5, like small amounts, our whole body goes into like shock. Like when you eat a pepper and you don't have enough, like that's why it makes a difference what you've eaten just before you have the pepper, right? Does the reaction take place within your mouth or within your stomach, right? Your stomach can handle higher acidic qualities than your mouth. So a lot of like really adept pepper eaters prep themselves with something that prevents that reaction taking place in your mouth. All right, so anyway, weak acids partially dissociate. So vinegar, right, or acetic acid, better known as. And that's what's really funny is a lot of these things, they're chemicals, but we eat acetic acid, right? You put oil and vinegar on a salad, we don't have a problem with that. Why? Because it's not a strong dissociator. It doesn't have it doesn't change your pH very much. It takes an awful lot of acetic acid to change your pH. Right? Weak bases, they also partially produce OH. So if you don't want to swamp something in hydroxide, right? You use a weak base. If you don't want to swamp something in protons, you use a weak acid, right? Because every time you use a proton, only a few more come off. Whereas in a strong acid, you're in a sea of protons, you can't control the release because it's all dissociated. But when you have a small amount and you dissociate, now you can do something with that. Any molecular compound that isn't an acid or a base is usually a non-electrolyte. Huh. So if you don't move electrons around, you're usually a non-electrolyte. You're a molecule, right? You're like sugar, a fat, or something. All right. What is the net ionic reaction? Oh, look, another one. What is the net ionic reaction between nitric acid and calcium hydroxide? So nitric acid, HNO3, calcium, alkali earth metal, charge +2, with hydroxide, -1 anion, so we're going to be 2 of those. And the telltale sign between acid and base is neutralization or the formation of water. So we're going to do 2H+, 2NO3-, calcium 2+, 2 hydroxide ions, calcium 2+, 2NO3, 2H+, 2OH-. What? We combine that to say it's water. Yeah, you almost thought you had me, huh?
Yeah.
Yeah, not going to happen today. So the water is the precipitate in this reaction. So guess what? Acid-base reactions are neutralization reactions, acid-base reactions, and double displacement reactions. How about that? And we cross out our spectators because water wants to be alone, does not want anybody watching. H+, OH-, H2O, liquid form. That's the net ionic equation, right? H+, OH-. That's what the neutralization is, the formation of water. So generally, strong acids and bases and their products do not appear in the net ionic equation. Only water does, right? So this is why it's so easy to neutralize acids and bases, is because they form water. So you put the same amount of H+ and the same amount of OH- into any strong acid, and you can make water and then just make patty cakes. I wouldn't suggest it because you don't know that it's completely neutral, but you could test it with a pH strip and then patty cake, but you're gonna have gloves on, so, and goggles,
Hang on.
and goggles, PPE, and masks, some of you. I don't, and those of you that are wearing masks, please don't stop wearing them, right? Because I'm a goofball. I don't mean anything by it. I fully support whatever you're doing, and I 100%. And that's when I was growing up. Here we go again. When I was growing up, right, differences were approved of and noted, and we, like, acceptance and tolerance was not conforming. It was accepting that people don't conform. That's tolerance and acceptance. So I know that definition has changed, but it's hard for old guys. We get so much experience and so little understanding. All right, so if we do acetic acid, which only partially separates, right? We have the same deal. We form water with the part that associates. And the more water we form, the more dissociates, right? Because it's only stopping separation because there's an H+ concentration being made. So if you put that together with a OH, you keep pulling off H+. That's what makes a buffer, right? Because you can pull off some H+, and then you can pull off more, but the pH stays the same because it only dissociates enough to have that amount, all right? Generally, weak acids and bases and their products appear in net ionic equations, right? Did you see that? That's the difference. How can you tell if it's a strong acid? It doesn't appear. How can you tell if it's a weak acid? It does. Because it changes, right? Started as an acid, and it dissociated, and it's changed to make water. And you can make this go back and forth depending on what you do. So what are the total and net ionic equations for the reaction between acetic acid and ammonia and water? So these are two what? Weak acid, a weak acid and a weak base. So you would have thought ammonia is a strong base, but it is not. It is only partially dissociates. All right, so we have our acetic acid and our ammonia. We put them together. We make acetate and ammonium. All right. Then we have our net ionic equation. We have our acetic acid plus ammonia. It stays exactly the same. Interesting. All right. No spectator ions. Everybody's part of the game. Okay, the general form of acid-base reactions, we have an acid plus a base, and we form a salt in water. And the salt is what? Soluble. Right? So we have HX, MOH, right? And usually that's a metal, and then we form the metal salt in the double displacement. Right? So double displacement we should recognize. Make sure you can take, don't ever swap cations and cations. Don't put cations and cations together. They repel anyway. Anions and anions repel. So don't have the second, the X and the OH go together, and don't have the H and the M go together, right? Don't have the H and the M go together because they're cations and they would not go together. Only H and OH and X and M go together, and the MX makes the salt, so a metal salt. And remember, if you make salt, it's if you make water, it's a neutralization because you're neutralizing the acid or the base, making them not have free H plus or OH minus. Acid-base reactions occur with more than just ionic hydroxide acting as the base. What? Yeah, there are other things that accept protons. For example, you have hydrochloric acid, and the blues go together, and the reds go together. And sodium chloride, right? Sodium chloride and hydrogen sulfide, which would be hydrosulfuric acid, not sulfuric, sulfonic, because it's sulfur and we change it to an I, because it's a binary acid. HNO3, nitric acid, plus sodium bicarbonate, we form sodium nitrate, which we know is soluble because all nitrates are soluble, and H2CO3, or carbonic acid, which dissociates into CO2 and water. It's another one of those that's always in equilibrium, and it'll give off CO2 gas. So when nature forms carbonic acid, it's also giving off CO2 gas. Lots of things in nature make CO2, and trees eat it up, and plants eat it up. Humans not so much. So sulfur 2- and bicarbonate are the bases in this case. So be able to recognize that. Oh, and just a note, this information is not in your textbook. Ha! There you go. Little added bonus for being here. All right, so we would do that, and let's just stop there. That's plenty for today. Good work, people. Thanks for bearing with me. Especially